everyone. Today, I will discuss about accessing desirability of highway project proposal and elements of highway traffic analysis. But I am not the only one to discuss it because two of my classmates, Bea and Rezaline, will be joining us. So let's start the discussion.
Economic appraisal of highway. What is economic appraisal? It examines the project contribution to economy of a region or country. It assesses whether the project increases the net wealth of a region or country as a whole or not. Economic appraisal techniques can be used to justify a scheme in absolute terms, in which cases the decision is made on the basis of whether the project is economically efficient or not. The cost-benefit analysis. It is the method usually adopted for economic evaluation of highway schemes. It utilizes the net present value technique, where the costs and benefits of the scheme are discounted over time so that they represent present-day values. There are different steps in cost-benefit analysis. Those are identification of the main project options, identification of all relevant costs and benefits, economic life, residual values and discount rate, use of economic indicators to assess basic economic viability, and the advantages and disadvantages of cost-benefit analysis. Identification of the main project option. This is the fundamental step in CBA process, where the decision makers compile a list of all relevant feasible options that they wish to be assessed. Many procedures for both identifying and defining project options. These include drawing on the personal experience of the decision maker himself, as well as the other expert in the highway engineering field, making comparisons between the current decision problem and ones previously solved in a successful manner, and examining all relevant literature. The next step, identification of all relevant costs and benefits. The application of cost-benefit assessment in the highway area is made more complicated by the wide array of the benefits associated with a given road initiative, some easier to translate into monetary values than others. Many of the benefits of improvements to transport projects equate to decrease in the cost. The primary groupings that contains this type of economic gain is termed user benefit, the reduction in vehicle operating cost, saving in time, and the reduction in the frequency of the accidents. Re- Reduction in vehicle operating costs. These constitute the most direct potential benefit derived from a new or upgraded highway project. It is often the most important one and the one easiest to measure in money terms. Savings in time. The upgrading of a highway installation will be invariably reduce travel time as well as improving the reliability of transport services. It has two steps in accessing the economic benefit of accident reduction. Entails. In the case of highway, this required a comparison of the accident rate on the existing unimproved highway with that of other highways elsewhere in the country, constructed to the higher standard of the proposed new road. The second step involves the monetary valuation of the accident reduction. There are three types of damage to be considered. First, property damage. Second, personal injuries arising from the serious accident. And the third one, the fatal accidents. The next step, economic life residual values and the discount rate. A highway project is often complex and long-term, with the costs and benefits associated with it occurring over a long time frame, which we term the life of the project. Given the transport development projects have the potential to be in service for a very long time, it may seem impossible to set a limit on the life of the project with any degree of certainty. If the technique is applied after relatively a small number of years, the project may well have to be assigned in a substantial residual or salvage value. In addition to this, the costs and benefits occur at different times over this time horizon. Because of this, they cannot be directly combined until they are reduced to a common time frame. This is achieved using another parameter, that is the discount rate. Next is the use of economic indicators to assess basic economic viability. Once the two parameters of project life and discount rate are set in place, these allow all costs and benefits to be directly compared at the same point in time. There are three techniques can be used for this purpose. First is the net present value or the NPV. Second is the internal rate of return or the IRR. The third is the benefit over cost ratio or the B over C. Net present value or the NPV. The NPV will estimate the economic worth of the project in terms of present worth of the total net benefits. The calculation is NPV is equal to the sum times the future cash flow times the PBC at the percent minus the PBCO. This is an example of net present value analysis in 5% and 10% discount rates. Internal rate of return or the IRR. It will give for each option under consideration the rate at which the net present value for it equals 0. The calculation is presented below. It is the example in solving the internal rate of return using the Excel. Benefits over the cost ratio or the B over C. Ratio, ratio based on the ratio of the present value of the benefits to the present value of the cost. The calculation, benefit cost ratio is equal to the PV of benefit expected from the project over the PV of the cost of the project. It, this is another example from Excel in solving the benefit cost ratio. Proceed tayo sa advantages and disadvantages of the cost-benefit analysis. Advantages. The use of a common unit of measurement, money, facilities, comparison between alternative highway proposal and hence aid the decision-making process. It given the focuses of the method is on benefits and cost the highway in question to the community as a whole. Disadvantages. The primary basis for constructing a highway project may be a societal or environmental rather than an economic one. If the decision is based solely on economic factors, however, an incorrect decision may result from the confusion of original primary purpose of proposed project with its secondary consequences.
Payback analysis is a method useful in evaluating proposals, such as privately funded highway projects. This method delivers an estimate of length of time taken for the project to recoup its construction cost. So the basic formula is NP is equal to CO over NAS, where NP is the payback period, CO is the initial construction cost of highway project, and NAS is the net annual savings. For the example problem, the developer is faced with choice between two development alternatives for a toll bridge project, one large-scale proposal and the other less costly but with smaller traffic capacity. So we are asked to calculate the payback period and check the result against the net present value. For the payback period, we have computed that option A takes 5.4 years to recoup, while option B is 6.25 years. So we can see that option A is a cheaper option because it can recoup in nearly 1 year or less. For the present worth, we can see that option B is a much more preferred option because the present value is over twice option A. So before, the environmental impacts of highway schemes are not even taken into account. But then, starting 1960s, there arose a environmental impact assessment wherein the National Environmental Policy Act prescribes a format requiring the developer to assess the following: probable environmental impact, unavoidable environmental impact, alternative options, short-run and long-run effects, and any irreversible commitment of resources. So, within UK in 1993, the Design Manual for Roads and Bridges provided format within which the environmental assessment of highway schemes has taken place. For air quality, we are assessing the main vehicle pollutants, which are carbon monoxide, oxides of nitrogen, hydrocarbons, lead, and carbon dioxide. For cultural heritage, the demolition and disturbance of archaeological remains, ancient monuments, and the like. For the construction disturbance, nuances such as dirt, increased levels of noise, and vibration. We are also taking into account the negative impacts of highway scheme to wildlife species and environment, and the way it alters the construction or the landscape, and how it reduces farmlands, because it is mainly used for construction of highways. We are also assessing how the construction of roadways affect the water quality and drainage, as well as how it destabilizes soil structure, and a highway proposal must be compatible with highway development plans at local, regional, and national level. NATA, or the new approach to appraisal, just managed to include five, which is environmental impacts, safety, economy, accessibility, and integration. Wherein, for the environmental impacts, they just make it more generalized. The basic elements of highway traffic analysis is we are determining the functional effectiveness wherein it's measured in terms of ability to assist and accommodate vehicles. So these are the concepts. For the speed flow and density of stream of traffic, the relationship is that traffic flow is equal to speed times density. Speed density relationship, as you can see, when density is at 0, there is higher speed. For flow density at maximum flow is equal to half of the jam density. And then speed at maximum flow is equal to half of the flow speed.
And I will be discussing about determining the capacity of highway. There are two different approaches to determine the highway capacity. The first approach is level of service, and the second approach is used in Britain. Level of service approach describes in a qualitative way the operational conditions for traffic from the viewpoint of the road users. There are 6 levels of service approach, ranging from Service A to Service F. Service A represent free flow conditions where traffic flow is virtually zero. Service B represents reasonable free flow conditions. Service C deliver stable flow conditions. Service D, the highway is operating at high density levels but stable flow still prevails. Service E represent the level at which the capacity of the highway has been reached. And Service F describes a state of breakdown or forced flow with flows exceeding capacity. In this figure, it shows the conditions and their associated speeds and flows. It is the linkage between level of service, speed, and flow capacity. In order to determine the road's level of service, a comprehension of the relationship between hourly volume, peak hour factors, and service flow. Hourly volume is the highest hourly volume within a 24-hour period. Peak hour factor is the ratio of hourly volume to the peak 15 minutes enlarged to an hourly volume. Service flow is the peak 15 minutes flow enlarged to an hourly volume. Maximum service flow rate for multi-lane highways. Given the existence of ideal conditions, the maximum service flow rate can be defined as where n is the number of lanes in each direction. C sub j is the capacity of a standard highway lane for a given design speed j. In table 4.1, it shows the value of C sub j for different design speed. In Table 4.2, it shows the maximum ratios of flow to the capacity of each level of service and design speed limit. For non-ideal condition, heavy vehicles such as trucks, buses, and recreational vehicles have a negative effect on the capacity of a highway due to their physical size, together with their relatively slow acceleration and braking. In Table 4.3, it gives the adjustment factors for a 4-lane divided multi-lane highway. PECE for trucks, buses, and recreational vehicles are defined for 3 different classes of terrain. Level terrain. This is categorized as gradients or horizontal vertical alignments that allow heavy vehicles to maintain the same speed as private cars. Next is rolling terrain. Those gradients are horizontal alignments that results in the speed of the heavy vehicle in question being lowered to a value substantially below those of the private cars on the same stretch of roadway. Lastly is mountainous terrain. Those gradients are horizontal alignment that results in the heavy vehicle operating at its maximum speed for a substantial distance. In this table, it shows the value given by the Transportation Research Board. Having obtained the necessary PCE evaluations, the overall correction factor can be estimated once the percentages of the 3 vehicle types present along the section of road in question has been arrived. P sub T, percentage of trucks in traffic stream, P sub B, percentage of buses in traffic stream, and P sub R, percentage of recreational vehicles in traffic stream. Given these values, the correction factor can be derived as follows. Maximum service flow rates for 2-lane highways. Where 1 lane is available for traffic in each direction, a classification of 2-lane highways applies. Sizing a road using the highway capacity manual approach. When sizing a new roadway, a desired level of service is chosen by the designer. This value is then used in conjunction with the designed traffic volume in order to select any appropriate cross-section for the highway. Within the US, it is a common practice to seek a peak hour between the 10th and the 50th highest volume hour of the year, with the 30th highest the most widely used. In order to derive this value for a highway, the annual average daily traffic for the highway is multiplied by a term called K factor such that where the value of K sub I corresponds to the highest annual hourly volume. Typical values for roadway are K1, the value corresponding to the highest hourly volume, is equals to 0.15, and K30 is equals to 0.12. DHV is two-directional flow. The flow in the peak direction is estimated by multiplying it by a directional factor D. Estimation of AADT for a rural road in its year of opening. Traffic was split into the following 5 categories. Cars includes taxi, minibuses, and camper vans. Light goods vehicles, excluding those with twin rear tires. Other goods vehicles with either 2-axle with twin rear tires, 3-axle rigid, or miscellaneous vehicles such as ambulances and tractors. Other goods vehicles, all goods vehicles with either 3-axle articulated or 4 or more axle. Buses and coaches, buses and minibuses with a capacity of more than 6 passengers. That's